Hello, physics students. This is Dr. Brenzi, and this is lesson 7.2.4. And our objective for this lesson is that we're going to be able to calculate the displacement of a simple harmonic oscillator when we apply additional forces. So the first type of force I want to talk about that we can apply in addition to the spring force right here, negative kx, is actually another force which is actually proportional to the velocity of our mass, and it's negative, so it acts against the velocity of the object. And you might ask yourself, well, how in the world do we do this in real life? Well, actually, a piston that is inside a very viscous fluid, and when I say viscous, I mean something that is thick like honey or molasses or something like that. Those are all examples of viscous fluid, and then when you try to drive a piston through that viscous fluid, the faster you try to drive it, the more it resists. So that's an example of a force where that is proportional to velocity but resists velocity and goes in the other direction. Another real-life example, if you look underneath your car, you're going to see shocks down there. Well, shocks operate on the same principle, and they do the exact same thing that we want to do in this spring, and we're going to find out what that is in this lecture. So you have a real-life looking system over here on the left, and then on the right, if you were to actually try to sketch it on paper, just want to give you some useful symbols that you might want to use at some point if you're trying to sketch or if you're reading sketches. This squiggly line right here, that represents a spring. You could probably figure that one out. And then this thing down here represents a piston that's providing this negative B times V force. All right, so when we have our new force is equal to negative kx minus B times V, well, we remember that force is equal to mass times acceleration, and acceleration is x double prime. So now we have a differential equation that says mx double prime is equal to negative kx minus bx prime. And then if you were to solve for solve for x double prime, you would get this equation right here. Pretty tough differential equation. It turns out that its solution looks something like this. It looks like an exponential decay, e to the minus, and then we actually have an interesting new letter here. That letter is called zeta, times this thing called omega n, and I'm going to describe all these, but you have an exponential function, and then you multiply that times cosine of omega, but it's omega d, and I'm going to explain what that is in a moment, times t plus phi. So it's like cosine and an exponential decay multiplied together. And that causes some very interesting things to occur. But let me define a lot of these new symbols that you're seeing here. This omega n, you'll notice that's equal to the square root of k over m. That is the omega, the angular frequency of a spring that has not been damped. So before we put this piston on there, this was what its angular frequency was, and we call this the natural frequency. Because that's the frequency that it would have if we hadn't messed everything up and put a piston on here. This Greek letter is called zeta, Z-E-T-A. Okay, and there's no special name for this variable, but what I will show you or point out is that it gets stronger the stronger that our viscosity gets. So the more that we can resist the velocity of our object, the larger this value gets. Okay, so when this is high, we have a very strong damping force. And then we have something called omega d. Notice that omega n is not in here. It's not the natural frequency now, but we have a damped frequency. That's exactly what this is called. Omega d is called the damped frequency. So the damped frequency is equal to the natural frequency times the square root of 1 minus zeta squared. So you'll notice that this number has to be less than 1, which means that omega d has to be less than omega n. So just the act of putting this piston in there has done some really interesting things to our motion of our mass. So what are some of these interesting things that happen? Well, first of all, we know that the amplitude of our motion now decays over time. So I could actually, if I were to plot the displacement versus time for our new system, you'll notice that its amplitude decreases over time. And what I could do is I could take my cosine and I could wrap it in an envelope right here, and this envelope is actually e to the negative zeta omega n times t. So our amplitude is decaying exponentially over time. Another thing is that the motion is no longer periodic. You'll notice that we were able to complete our first cycle by the time our time reaches 1 right here. But if you go over here, you'll notice that when we go from 3 to 4, we haven't completed a cycle at all. So in a sense, the motion is no longer periodic. We can't count on the peaks happening at 1, 2, 3, 4. Okay? We can't count on that anymore, so the motion is no longer periodic. Well, what other interesting things happen? I mentioned this already when I defined what the damped frequency is, but the damped frequency is actually lower than the natural frequency of our undamped spring. So before we put that piston on there, we had a frequency equal to the square root of k over m, but when we put that piston on there, it actually operates at a lower frequency than what we originally had. Well, what's the final interesting thing that happens? Well, maybe not the final thing, but the final thing I'm going to list here is that you can have something called critical damping and overdamping. So if we take a closer look at this equation right here, where we are looking at our damped frequency, you'll notice that this number can be negative. Well, this number ends up being negative when zeta, or zeta squared actually, is greater than 1, which means that when zeta is greater than 1, we have this number become negative, which means that this whole damped frequency thing becomes imaginary and something crazy happens. Well, that crazy thing that happens is this. Now, when we have zeta less than 1, in other words, our damping isn't very strong, we get the same behavior that I showed you on the previous graph. We have like a cosine-like behavior whose amplitude decreases exponentially. But if zeta ends up equaling 1, then we can get what's called critical damping. And that is that this is the maximum, or actually the minimum amount of time where this can go from our starting position and decay down to a value close to 0. Okay, so it's almost like a very efficient exponential decay. And then when you get overdamping, which means that zeta is greater than 1, then you get this much slower exponential decay, and you'll notice that no oscillations are taking place anymore. We're not going back and forth anymore. We're just slowly decaying down to 0. So that's what can happen if your damping gets too strong. Okay, so damping is one phenomenon that can occur that when you add force to a spring, add outside force, and that force was proportional to velocity, but acting in the opposite direction. Now, you can do something else, and this produces some other interesting behavior. So let's say that we decide to drive this thing with a sinusoidal force. In other words, we are grabbing this thing, and then we're deciding, okay, I am going to grab this thing, and I'm going to apply a force that is sinusoidal in nature. So I'm going to push it forward, drive it back, and then push it, pull it, push it, pull it, push it, pull it, like this. And I'm going to keep on doing it, and I'm going to pick a driving frequency that I do that at. I don't care what this is. I don't care what that is. I'm just going to go ahead and pick my frequency. It could be motion that's kind of slow like this, but it could be a motion that's very fast like this, or it could be motion that's very, very slow like this. Okay. Well, a couple of interesting things happen. Let's see, I had something here. Oh, yeah. As you're taking notes here, I noticed that when I originally typed this up, I put omega D and omega D here, but I realized then that I need to change that because I just said that omega D is a damped frequency, but that's not true because I can actually choose what frequency I want to drive this thing at. So I'm going to call this omega F. So if you just wrote this down as omega D, change it to omega F, please. All right. So, well, one interesting thing that happens is that the displacement changes its behavior. It no longer depends on no longer depends on the stiffness of the spring, doesn't depend on the mass that I'm working with. It no longer depends on how strong that piston is. The frequency of my displacement equation is going to have something that looks like x is equal to a times sine or cosine of omega f times t. So the frequency of my displacement is totally going to be determined by how fast my driving force is going. So that's one interesting thing, is once we pick up this mass and start shaking it, we get to determine what its frequency is. It doesn't depend on the spring, doesn't depend on the damper, or doesn't depend on the mass. Kind of seems pretty intuitive, but you know, until you actually work through the equations and actually think about it, you don't come to that intuition. Now, here's another really interesting thing that happens. There's something that happens to the amplitude of our displacement. In other words, how high or low this thing can go above equilibrium. Okay, so if I'm going up and down like this, of course, this is the amplitude A of my displacement. And that amplitude, it depends on a lot of things. It depends on the maximum force I exert with my hands when I've grabbed that mass. Depends on the mass, depends on the natural frequency, it depends on my driving frequency, and it depends on the dampener. Now, something really interesting happens if I choose to drive my force with an angular frequency that's approximately equal to the natural frequency, and remember that's equal to the square root of k over m. So if I choose to drive this with the same frequency that is its natural frequency, in other words, what frequency would it go if it were just a spring and I just let it go, then it turns out that the amplitude becomes approximately the maximum force divided by the strength of my dampener times the angular frequency of my driving force. Now you might be thinking to yourself, well, that doesn't seem like such a big deal, but Look at what happens when B gets very small. What happens to A? Well, A is going to get really huge, which means that if I don't have a very strong dampener on this, this amplitude is going to get very, very large. And that's exactly what this graph is telling us right here. Okay, so what you see on this graph is you see amplitude, A. So the amplitude of our displacement. And along this axis, you see omega. It's actually omega F divided by omega N. Okay. Now, when omega F is approximately equal to omega N, that means that this axis is going to be 1.0. And you'll notice that the amplitude reaches a peak. And it can get quite large, especially if I have a dampener that is not very strong. So the larger the dampening gets, the smaller this peak gets. And as a matter of fact, I can completely eliminate this strong, what's called resonance, by having enough dampening such that this B is greater than the square root of 2km. So amplitudes can get quite large when you don't have much dampening and when you drive your force at approximately the same frequency as the natural frequency. In real life, what does that look like? Well, one example, one real life example might be a video that you have seen in the past, and that is a video of the Tacoma Narrows Bridge collapsing. Now, there's never been an official report of what happened and what caused the collapse of this bridge, but you definitely see that this thing is twisting, and that the longer this thing is allowed to twist, the bigger the amplitude of the twist becomes. Well, that's an example of what's called resonance. So, what ended up happening probably is that the engineers failed to design this bridge so that that resonance would be damped out. And because they failed to do that, when the wind hit it at just the right angle and at just the right speed, it caused the amplitude to go really, really high. And so you're starting to see a lot of twisting motion. And then eventually the cables that were supporting the bridge couldn't handle it, and everything fell apart after about 45 minutes of this twisting motion. I'm going to show you another example of resonance frequency and resonance in class. But for now, hopefully you get an idea of some interesting things that can happen when we decide to add some more forces onto our spring force. I think they're really interesting, and they make physics like really super fun and really super deep. So I'm looking forward to working on that with you guys in class, and I'll see you soon. Bye.